Okay, welcome to Chemistry 111. We'll go ahead and continue where we left off. Quick reminder, where we left off was right here. We just briefly talked about the international system of units and our base prefixes. We're going to be using these when we convert one metric unit to another. So you definitely need to learn pretty much by heart the ones underlined. Some of the ones not underlined probably aren't going to come up in any problems. They might hypothetically get asked on the homework, but I typically don't ask those non-underlined ones on the test. There's many different ways to try to remember them. For that, we'll get to some of the math actually today. Oh, come on. Okay. One of the things we'll be using these for is for what's called a derived unit. A derived unit is basically a unit that is a combination of one or two international SI units. The most common one we'll be using is volume. We don't really have an SI unit for volume, but volume can be derived from just distance, our distance of meters. So volume, remember, is the space taken up by matter, and that would be, of course, length by width by height. And so if I do it length in meters, width in meters, and height in meters, meters times meters times meters would become meters cubed. However, another common unit of volume we will use will be liters. It's a way we can measure a volume of a liquid more commonly than, say, the volume of, say, a solid. But, and there is a conversion between the two that I will show you. One of the most common conversions for people who have ever listened to any like medical drama is 1 milliliter is equal to a cubic centimeter. So centimeters by centimeters by centimeters. So if you ever hear the term cc, that stands for cubic centimeter. So if this doctor says, oh, give me 5 cc's of morphine, then what he's saying is just 5 milliliters, just telling you what volume of morphine are we injecting. Density, not always the most useful one, but it's one that will be used pretty commonly for this chapter because, it's a pretty easy math we can do. But density is defined as the mass over the volume. Now, if we use the proper SI units, it would be kilogram over meter cubed. And the equation is density, the m over v. But we'll learn various different ways to treat this. But density is an example, remember, of an intrinsic property, one that doesn't depend on the amount of substance. Density should be constant throughout. Now, these next couple are a little bit more physics style terms. We're not going to see them quite as often, but we will see them occasionally. Velocity, which is a distance traveled over a time, which would then using the SI units of distance and time, meters per second. And of course, acceleration, which is the velocity change in a given time, which would be then meters per second divided, which would be meters per second squared. The basic premise here is when you take two units and multiply them together, you essentially raise it to the exponent of the number of units we have. So if I have meters by meters, I'd get meters squared. If I get 1 over second times 1 over second, I'm going to get 1 over second squared. And occasionally, now this is not going to be as common, but occasionally we will have units that convert into other units. It's a common thing in physics and happens occasionally in chemistry. Things like force units. In physics, you might be measuring a force as a Newton, but a force is actually a mass times acceleration. So mass is kilograms. Acceleration, as I just said, is meters per second squared. So if you get a unit of kilogram times meters over seconds squared, that is equal to a Newton. And energy, which is one we will use quite often, is actually another physics swap. We're going to measure energy as a joule, but a joule is derived from a force applied over a distance. So I put a Newton force and I push it some amount of distance. So taking that kilograms times meters per second squared times another meter, you get kilogram meter squared per second squared, which is equal to a joule. Said, don't worry about these too much. This is just, I'm trying to throw out some examples of what you could see. The most common one we'll have to worry about is density for this chapter. But then one that we will see later on in the semester, but that's not going to be till like test 2 or 3, is frequency, which is measured commonly in hertz, but it's also measured in inverse seconds. So 1 over seconds. It's typically used for waves. How many waves will travel through a given distance and how long will it take a wave to repeat? And so you're measuring it in kind of like a unitless waves per second. And so the per second is where you get the frequency. But you may have also seen that as 1 per second is equal to a hertz. So if you ever look at your headphones or speaker, you'll be often given a unit of measurement on there as hertz, like how fast can the sound waves come out? Telling you essentially something about the audio quality of your things, like how well can they differentiate different, if the music comes too fast, can it produce all the sounds you need to produce? Well, okay, so here's where we actually start to need our calculators. I'm going to go through some of the basics of our calculators, but we need to be able to use our calculators on a regular basis. So you want to start bringing this, it'd be great if you can actually work along with me. If you can, that will allow us to see if you can get what I'm getting on the screen. That means you should be able to get it on the homework later. And if you're not getting what I'm getting, I can ideally pause and try to help you if I can see what you got, or at least what functions you punched into your calculator. So having a calculator that is semi-programmable, or at least shows you what you've all typed in, is very helpful, because sometimes order of operations is killer. You got to know how your calculator works, how your calculator understands the math, so that when you do this, you don't end up punching in something in the wrong order and confusing the calculator. Because how we write it on the board, how we write it on the paper, is not always how we type it in the calculator, because the calculator is dumb. It does that, like exponent, parentheses, multiplication, division, addition, subtraction. So it's always going to, what was it, parentheses, I can't remember the exact order, but the idea is like you work your way out towards in. And if you do it, punch things the wrong order, or don't have a parentheses here, it can totally mess things up. So one thing we'll get used to is scientific notation. Because often in chemistry, we're working with the subatomic and turning it into the macroscopic, turning something from too small to see into something you can hold in your hand. And so we'll use really big numbers and really small numbers, depending on what scale we're dealing with. And so scientific notation is going to help us. Otherwise, you read this number, 602 sextillion, 200, pentillion, is really impractical to write. You miss a 0 and your answer goes wrong. It's like there's literally 6 with 23 digits after it. 6.02 times 022 times 10 to the 23rd. So just a quick reminder, standard scientific notation is you have some number C times 10 raised to a power. C is the unit with all the significant figures. It's written as a number between 1 and 10, and n is the number of decimal places you have to move it to the left or right. If n is positive, you move the decimal to the right. If n is negative, you move the decimal to the left. So if I have, example, 523, this one is not super useful to turn into scientific, but it's perfect. So I need a number between 1 and 10. 5 sorts that. So I'm going to put the decimal at 5, right after the 5. So 5.23. I had the 0 point would be right here, so I had to move the decimal 2 to the left. So to get it back, I'd move it 2 to the right, so it's 10 to the second. 10 to the second. So it's 5.23 times 10 to the second. Now this one, 0.00026. I want to get this between 1 and 10, so 2.6 is between 1 and 10. And I'm going to move the decimal. I have to move it 1, 2, 3, 4 places to get it there. So that's 10 to the negative fourth. So hopefully this is reminding us of whatever math we've taken in the past, hopefully. But I want us to be sure we're all in the same spot, which is why I'm going from the very beginning. Now, how do we actually punch those into your calculator? You could literally say 5.23 times 10 caret 2. But there's often easier ways to do that, depending on what calculator you have. So when you have a chance later, if you don't have a calculator on you right now, look at your calculator. You could either look at it as the area with the inverse log, the second log function. You might also have, if you have a 3-function if you have a graphing calculator, you might have a button labeled EE. You might have a button labeled exponential. You might have a number x10n. It all depends. But EE is just a shortcut for saying times 10 raised caret something. So if I was to type this in my graphing calculator, I would say 5.23. I hit the EE and then just 2. I don't need the times 10 caret before the 2 because the EE serves that purpose. Same way, if I want 2.6 times 10 to the negative fourth, I can say 2.6 EE button. And then I have to make it negative 4. Now, because of that, if you see me write on the board, I will often do this. I might write 2.6 E negative 4. That is how your calculator will tend to write a number like this. It will tend to do that with that E showing how many places to move it left or right. So that E, all that E stands for, that E is our times 10 raised to whatever. So I'm not sure. We write that. This is more visible on screen. That E, as I said, equals the times 10 raised to whatever power. So if you ever see me do that, that is what I'm trying to express. So don't be overly confused if that's what I end up doing. Now, these next few rules, if math is not your strong suit, don't worry about it. You don't have to apply these rules. You can always punch this into your calculator. Though if you do understand math reasonably well, you can use this to check your answer and see if your answer seems reasonable. Said, use it if you want. Don't feel you have to use these. But a few rules will help us check. If you're multiplying two numbers with exponents, it's the same as adding those two exponents together. So if I take 10 to the fourth times 10 to the third, it becomes 4 plus 3, 10 to the seventh. So if you punch it into your calculator and you get 10 to the first, even if you don't know it's 10 to the seventh, you should know it should have gone up and go, I must have goofed something. If I take 10 to the fourth times 10 to the negative first, it should go down to 10 to the third because I'm adding a 4 and a negative 1. Dividing is the same as subtracting. So if I have 10 to the ninth divided by 10 to the third, it becomes 9 minus 3, or 10 to the sixth. So you can kind of tell, is this number looking right when you punch it into your calculator based on how big or small it should be. And if you raise a number to an exponent, it's the same as multiplying by that exponent. So 10 to the a, so like 10 to the third raised to the power of 4 means 10 to the third plus 10 to the third plus 10 to the third plus 10 to the third, or 10 to the 12th. And the same way is if you root it, you divide by that. So if I square root 10 to the fourth, 10 to the fourth divided by 2 is 2. 4 divided by 2 is 2. So as I said, you don't have to use these. This is just there. If this is something you feel you can do, it will help you tell, did I punch this into my calculator right or wrong? And it can help you check a number before you try to solve for something. Okay, so this is the hardest part of this chapter when we go into sig figs and significant digits, and it's going to be the main thing we try to kind of cover in lab. It's the idea of how well do we know a given number. We like to say we know a number really well, but that's not always the case. So when we report a number, we can report it in one of two ways. We have two types of numbers: exact numbers. Exact numbers are numbers we know with no degree of uncertainty. This could be the only two exact numbers we'll really see is numbers that are something you can count. Like if I count the number of students in this room, that is an exact number. I do not have to approximate. There is no half students here. There is only our 6 students. There is no more, no less. And numbers that are definitions, like there is 12 inches in a foot. By definition, that is how many there is. There is no more, no less than 12 inches in a foot. If it's not 12 inches, it's not a foot. So by definition, those are exact numbers. Now, almost any other number, whether it's by measurement or reading off a piece of paper, will not be exact just because of life. These non-exact numbers could be just a measurement. If you measure this, it only goes out to so many significant figures. There's only so many marks on the ruler you can read it to. At some point, it becomes too small to determine the change. But it could be by approximation, like trying to count how many people are in a stadium, or how many people are attending an election, or how many people attend this protest. Unless there is literally a number small enough to count, they're going to have to find some way to approximate the actual number. So, and this is going to lead to what's called uncertainty. That's going to exist in almost all measured quantities. It could be uncertainty in whether a number is accurate, or uncertainty whether a number is precise. When I talk about accuracy, it's how close a value is to the correct answer. Sometimes this number is known, sometimes it's not known yet. So Accuracy, if you're saying how many people attended a march, how close to the actual number of attendance did you get? You may not actually ever find out whether your number is perfectly accurate or not if we don't actually physically count one by one by one. Precision has to do with how repeatable the value is. If I try to count the number of people there, and the first time I do it, I get 3,000 people. The second time I do it, I get 4,000 people. That's not very precise. Somehow I came up with 1,000 more people the second time around. It's how repeatable this is. Most often, precision is seen by looking at the standard deviation in your values. How close does your 2 or 3 or 4 trials come to within each other? Now, these layers of uncertainty could be just human error. They could be equipment error in the lab. They could just be the nature of like how you're calculating something. Whether you use a good balance or bad balance could determine what degree of uncertainty you have. You get a balance that only goes up to pounds, you're going to be limited on how accurately you can measure a mass. If you get a balance that measures in grams, grams are smaller than pounds, you could probably measure a little bit more accurately. If you get some that measures milligrams, you could get even more accurate, so on. But it's going to lead to the tough topic that I was talking about, significant figures. It's basically when we report a number, we are trying to report only numbers we know with some accuracy. A significant figure, a significant digit, is a number we can reliably state that we know. The last significant figure that's ever reported in a number has often been rounded up or rounded down, last known accurate place. So it means that the value just past that could essentially run 5 up or 5 down. That we don't know what the digit just past the sig fig actually is. Like saying, if I say, how many people attended the Super Bowl? You might be talking about, you might know accurately within several thousand, or even maybe several hundred. But do I know in the tens place how many people showed up? Not necessarily. Do I know in the ones place how many people showed up? Not necessarily. But I might know to the hundreds place. I might know to the thousands place. And so, now, when we have significant figures, it's much easier to lose them than it is to gain them, because when you add uncertainty to the mix, they will screw up where the significant figures are. Now, the problem is we're used to in math, you punch in a number, you get a long repeating decimal. You get a long repeating decimal and you're like, write down the whole thing. Well, significant figures actually says most of those are artifacts generated by the math. If you take a number divided by 7, you're going to get a really nasty string of numbers. 7 doesn't divide into many things very easily. So where do you stop recording? And usually we stop recording where the significant figures are. So we have to kind of figure that out. So when we write these numbers down, whether it's reading it off a piece of paper or measuring this off a ruler, every non-zero number are always going to be significant. The question of whether this number could be significant or not comes in the zeros. When we look at a zero, a significant zero tells me something about what it is, and a non-significant zero just tells me something about the size. So like a non-significant zero just says, this number very big or this number very small. It doesn't necessarily say, no, we actually know there is 0 people. if I know there's 30 people in a club, and I know there's exactly 30 people in the club, that's 30 tells me, oh, there's exactly 30. But if I say there's about 30 people in the club, it could be 32, could be 29. That zero essentially says it's close to 30. It's big like 30, but not exactly 30. So I know this is getting kind of philosophical with numbers, and that's not what we're taking chemistry for, to get some philosophy. But that's kind of what we're dealing with here. So we have to look at the circumstances here. Significant zeros will tell us something about the digit, non-significant are placeholders, signifying magnitude. So there's special rules whether you have a number that is with a decimal or without a decimal. When you have no decimal, you look to the last non-zero number and count left. So if I just said there's 15,000 fans at the stadium, I don't say 15,000 period. I just say there's 15,000 fans in the stands. It's essentially saying, I know there's about 15,000. Is it 15,100? If it's 15,020? We don't know, but we know it's approximately 15,000. It's either somewhere 14.5 or maybe it's 15.4. I don't know. Somewhere between those two rounding errors, it rounds to 15,000 fans. So every number to the right of that 5 is considered non-significant. What that means is if I was to report that in scientific notation, that would be a 1.5 times 10 to the 4th. I would only need the 1 and the 5 because those zeros don't really add anything into it. If I'm looking at a decimal, like the bug is 1 centimeter, 1.0 centimeter, and I want to turn that into meters, and I have a decimal, 0.010 meters. When you have a decimal, you find the first non-zero number and you go right. So without a decimal, we take the last and we go left. With a decimal, we take the first non-zero and go right. Because basically looking there, the 1.0 is saying it is exactly 1 centimeter and 0 millimeters. When you look at it in the meter form, that 0.0 basically tells us this is small. The 0 after that is there to say, I know this is 1, I know this is 0. But I don't know anything beyond that. So if you turn a number into scientific notation, all non-significant zeros are removed, but we keep any zero that is significant. So 5040, no decimal point. So no decimal point says we take the last non-zero, which is 4, and go left. So 5040 becomes 5.04. I had to move the decimal 1, 2, 3 places, so times 10 to the 3rd. So what that is basically saying, I know there is 5,000. I know there is 0 hundreds. I know there is 4 tens, but I don't know how many ones there are. It could be 4 ones. It could be -5 ones. It could be somewhere between 35 and 44, so that it rounds up or rounds down to 40. Excellent example is if you're looking at the active ingredient in your medicine. You're looking at how much actual active ingredient ibuprofen is there in that pill. They have to report so many significant figures. Depending on how that is, they don't know the actual amount of active ingredient can vary by a few milligrams one way or the other, depending on how they report that. Depending on how they report that, we don't actually know the exact amount. It's just on average, it is this amount. You might get a little bit more in one dose and a little bit less in the next, depending on how accurately they can report it. Now, so looking at this in general, so if I'm reporting this 340,500 C, what is that? What is that in terms of sig figs? So significant. So how would we report that in standard notation, and how many significant figures would we report? So is there a decimal or is there no decimal in that number? Say no decimal. So with no decimal, we look to the last non-zero number and we move left. So the last non-zero number is 5. So every number to the left of 5 is something we want to keep. Every number to the right of 5 is, one too many, something we will lose. So how many significant digits do we have? 1, 2, 3, 4. So to report this in significant scientific notation, put my decimal right here. I had to move my decimal 1, 2, 3, 4, 5. To move it 5 decimal places. So e to the 5th. Just looking at 3.405 e to the 5th. Looking at the next number, 0.00459. There is a decimal. So in this case, we take the first non-zero and count right. So how many sig figs do we have? Would have 1, 2, 3, 4. So we can just include everything to the right, including that 0. Now, when we turn that into scientific notation, I have to move the decimal 1, 2, 3 places, somewhere between the 4 and the 5. So that's e to the negative 3. 4.5 e to the negative 3. And then 3.04, it's one of those weird ones. 3.04, there is a decimal. So we take the first non-zero on the left, 3, count to the right, so there's 3 sig figs. All numbers are significant. There is no non-significant number. If we were to turn this into scientific notation, it just becomes 3.04 times 10 to the 0th power. 10 to the 0th power is the same as 10 to the first, is the same as 1. Any number raised to the 0th power is 1. So that one's a kind of silly one, but it's showing all. So there doesn't have to be a non-significant 0 in there. There doesn't have to be a non-significant 0 in there. Now, when we're dealing with these, We can lose these because we're going to be doing a lot of math with numbers that have varying degrees of accuracy. When we add or subtract these guys, multiply or divide with these guys, the degree of accuracy is going to carry over. If I add a big number that is not super accurate to a small number that is super accurate, you're going to lose that small number entirely. If I say I'm 250 pounds about, and then I pick up a cell phone or something like that and say, how much do I weigh now? Well, even if the cell phone is like 2-3 grams, if I know I'm about 250, that doesn't really change the scale at all, because you have something big and inaccurate plus something that's small and accurate, which is still about 250. It hasn't really changed any significance. So when we add and subtract, there is a rule. So we'll use this in practice. When we add and subtract, we figure out where is the last sig fig. We line these up like we're doing grade school math. I know it seems stupid, but it actually really helps. If you line these up like you're doing grade school math, where the decimals are over top of each other, you can draw a magical line behind the last significant figure on one of the numbers. Everything to the left of that line gets kept. Everything to the right of that line gets lost. And because of this, whether it's addition or subtraction, it's the same. But see here, I've lined up 3.40 and 0.054. If you do the math, just punch it into your calculator, you get 3.454. But that last 4 is an artifact, because every time you don't have a number there, that is an uncertain number. It's like a big question mark. It's like a stinky question mark. We don't know what that is. If you're adding a question mark to a 4, you add a dash of certainty to uncertainty, you're still left with uncertainty. So you're adding 4 and a question mark. We don't know if that 4 went up or that 4 went down. So we can no longer report accurately what that 4 was. We just say, whatever this was, this number either rounds to 3.45 or 3.46. We don't know exactly, but we know it rounds somewhere between 3.45 and 3.46. That's all we can safely report. In this case, 4,200, no decimal point, and 342, no decimal point. If I line them up where the decimal points would be, 4,200, I only know the 2 is significant. 342, the 3, the 4, the 2 is significant, but when these 2 zeros are like question marks, we don't know, is this high, is this low? So when I subtract this, you get 3858. However, you round up to the correct number of sig figs. So you round that to 39. We don't know if this is exactly 38 or 39. But we know it's close to that. We know it's close to 3,900. That's what we're saying. We cannot report, you can report 3858, but it's not quite right because we don't know for sure. When we multiply and divide, it becomes a bigger factor. And we're going to be multiplying and dividing far more than we do addition and subtraction. We will do addition and subtraction, but just not that often. So when we multiply and divide, we actually just keep the straight up number of sig figs. So what this is going to mean in the long run is you are going to want to, in lab, record as many decimal points as the number will allow for. If you're weighing something on a balance and it reads 5.000, you should write 5.000. You should not just write 5. If you're saying 5, I'm saying I have 1 sig fig. If you're saying 5.000, it means I know this is 5 to 4 significant digits. So you always do as much as you can, because we're going to keep the number of significant figures in the final answer. So if I take a number 45.0 times 1004 times 3.0, I have a 3 sig fig number. I have a 4 sig fig number. I have a 2 sig fig number. When I multiply them together, I get this big number. When I round it, I have to round to 2 significant figures. So the first number 1, the second number 3, that gets stayed behind, and then I go 5. 5 rounds up. So all I know is that this is somewhere along the range of 140,000 meters. All because I didn't know the 3.0 very accurately. If I knew this more accurately, if I knew this was 3.00, I could round it to 136,000 meters cubed. The more accurately you know this, the better you can report this. So it's one of those measure twice, cut once type things. The better you know this, the better you can figure out how much do we actually have to work with. So when we measure a volume, we want to record this as many significant figures as we can. If we record a mass on the balance, we want as many significant figures as we can, because that's going to change what we can use in the final number. Oh, sure. Okay. So in practice, I'm going to write these on the board. We'll go through them real quick. As I was trying to say, if you can't read this on here or you don't get it written, fine, I show the work up on the slides. I'll show the work, but it's usually I don't go through all the steps, so it's not quite the same. But okay, so there's that one. Let me write all of them on the board. 3, oh God, my markers. I need to get a new marker, 3.25 grams per mil times 0.035 mils. And the last one, 3504. 504. 31.4. Divided by 1.4. 1.404. Okay. Yeah, I need to get a fresh marker and clean this board really well. Okay, so the first one, we're adding these numbers together. I'm putting them all lined up. I said 1, 2, 3 digits. 1, 2, 3, 4 digits. I have to draw an imaginary line at the after the hundredths place, because right here, that's an unknown. We don't know what that is. So even though we're going to round from there, we can only keep everything to the left. So this becomes 2. Oh, come on. Marker's like absolutely dead or dying. Let's see. 2, that becomes 7. That becomes 7. The 4 gets rounded down. So I have the answer 7.72. On this one, we have 3.25. That is 1, that is 2, that is 3 sig figs. we have 0.035. So with that is 2 sig figs. So I'll do this multiplication, but knowing that at the end, we have to keep this as 2 sig figs. So my number, you do this, you get the full number. What the full number is 0.11375. Unfortunately, you can only keep the 1, So your number becomes 0.11 grams. That's a G. Now the last one, it's the hardest one here. We have to do a multi-step problem. We have to do the parentheses first and then divide. So we have 35.04 minus 31.4. So I'll take, and so that leaves a question mark. So we can only round it to the decimal place. So 35.04 minus 31.4 gives you 3.64. But we can only keep 3.6. You can only keep 3.6. Now, how you choose to do this shouldn't really matter for the most part. It doesn't change too much in the long run. You could either round it now or round it at the end. If you round it now, it might be easier because you can remember how many sig figs am I supposed to have. So I can say, oh, that's 3.6. When I take 3.6 divided by 1.404, whatever that answer is, I have to round that to 2 sig figs. So 3.6 divided by 1.404 would give you a full number of 2.564. But rounding that to 2 spots, that becomes 2.6 is my answer. 2.6. I said, if you can't read the board, well, tomorrow I'll have a better marker. We'll deal with that. But so we have to do it step by step. Well, that's as far as we can get for today. Tomorrow, or not tomorrow, we'll actually look at the big concept. As much as we may hate significant figures and think that these are hard, note that significant figures will play a minor annoyance through the rest of the semester, especially in the lab. But if you do not understand and get dimensional analysis, come see me, come get help. Because if you cannot get dimensional analysis, this will keep coming up. This is how I do the majority of the math. We have to understand this to be able to convert this or get that. Otherwise, it becomes memorization of equations, and that's not fun. So we need to make sure we understand dimensional analysis, which is the topic we are talking about on Friday. Thank you for your time.